A hot air balloon is tethered to the ground by two ropes. The ropes have a tension of 300 newtons each and are angled at 30 degrees from the vertical. The balloon has a mass of 200 kilograms, and we've been asked to find the buoyancy force acting on the balloon. Well, the first thing we do is draw our axis, which we'll call X, standing for the horizontal, and Y for the vertical. And we'll put a dot in the middle where the origin is to represent the balloon. And now what we've got to do is put in the forces round this dot, which is called really a free body diagram of the balloon, showing all the forces acting on the balloon. And the first force we're going to put in is obviously the buoyancy force, which is the force we've been asked to find. And that's acting straight up like that. The force acting straight down will be the weight of the balloon, which always acts vertically straight down like that. So we see that the buoyancy and the weight force are acting in the y-axis. Now we've got to put in the forces due to the tension in the rope. And that's this one here, 300 newtons at 30 degrees. And the right hand rope, that will be exactly identical as well. 300 newtons at 30 degrees to the vertical. Now all we have to do after that is to resolve the components of these vectors into the y-axis. Now to do that, I'll bring over the components of the 300 newtons due to the left hand rope, and that snuggles in there. So here we have the 300 newton tension vector, and here we have its horizontal component, and here we have its vertical component. And we can do the exact same for the other rope. We can show that exactly the same way. We can have the horizontal component and the vertical component. Now from the diagram, the two horizontal components are in opposite directions, so therefore they will cancel each other out, and therefore there will be no movement of the balloon either left to right, and that's what's happening. But it's these two vectors here, one on top of the other, which are the y components of the 300 newton vectors that we must take into consideration. So how do we find out that y component? Well, we do a little bit of trigonometry and we label one of the triangles. We have the angle here, 30 degrees, so opposite side of the triangle will be the opposite side. So we can label that bit in there, the opposite side. The side opposite the right angle of the triangle will be the hypotenuse. We can put that there. And finally we've got the adjacent to find. And it's the adjacent side of one of those triangles which is really the size of the y component of the force acting downwards. So let's find it out then. To find the adjacent side we have to use some trigonometry, and we know from our trigonometry relationships that cos of 30 degrees is going to be equal to the adjacent side divided by the hypotenuse side. Now the adjacent side will give a name. We'll call it the force acting down the way, we'll call it F. And we have to divide that by the hypotenuse, which is 300 newtons. A bit of cross multiplication, and we have the downward force F should equal 300 multiplied by cos of 30 degrees. So the downward component of the 300 newton force due to the left hand rope turns out to be 260 newtons. So that's the downward component of it. So if I just remove these labels and make the diagram a little bit simpler by taking away the labels, putting the two forces there, then I can replace the components of this force with the new one I worked out, 260 newtons straight the way down. So take away the components and I'll replace that with 260 newtons adding down the way like that. Because this component now, this vector, has now been reduced into its component form, so we can take it away. So we have 260 newtons down the way. Now the same thing happens for the 300 newtons force caused by the tension of the rope and the right hand rope. If we do the same calculation again, we get the y component of the force to be exactly equal to 260 newtons again. So we can remove that and put in with it its component like that. So now we've got all the forces aligned in the y-axis, and all we've got to do now is say the following. The buoyancy force, which we'll call B, acting upwards, must be equal to the sum of the forces acting downwards. So we've got two 260 Newton forces, so we're going to have 2 times 260 newtons, plus the weight of the object. Now we know the weight of the object, that's quite simple to do. The weight of the balloon is equal to the mass of the balloon times the gravitational field strength, which is 9.81. So the weight of the balloon is going to equal to the mass, 200, multiplied by 9.8. So the weight of the balloon is going to be given as 1960 newtons. So therefore we can substitute that into our equation here, and we get a value for the buoyancy force. Buoyancy force equals 2 times 260 newtons, which is going to give us 520, plus the weight of the balloon, which is 1960 newtons, and therefore we end up with the final answer that the buoyancy of the force, which is pushing the balloon up the way, is going to be equal to 2,480 newtons. So that's a very complicated balloon problem done by ropes at different angles to the vertical, and we have to use our components of those vectors to solve the problem.
Physics is wonderful. Physics is cool.